Hey everyone. Today we're going to do a problem where we are going to try and merge k sorted arrays into a single sorted array. And this is basically an extension on the fairly simple problem that you see when you're doing a merge sort, where you're just merging two arrays together into sorted order. But in this case, we're going to have some arbitrary number of arrays, and we're going to try and merge them all together. So if we look at this example here, we have the array 147, 258, and 369. And obviously this is just all the numbers from 1 to 9, so when we merge them all together, we get this sorted array that is 1 through 9. And that's what we would expect. And of course, you could change this around. You could make one of these have more values, one of them have less, different things like that, but that's the gist of the problem. So let's jump right in. The first thing we want to do always is clarify the problem with our interviewer, make sure that we ask any questions we might have. So one question that I have here is, are all of the arrays going to be the same length? What value of k should I expect in terms of like numbers of arrays, things like this, just to get a sense for the problem, because that could affect how we are actually going to solve the problem potentially. Because for example, if we know we're going to have a few number of very long arrays, that might lead to a different solution than if we have a lot of very short arrays. And so we could think about how this might affect the time complexity of the problem, or how it might affect our solution. In this case, it's going to be pretty arbitrary, so we don't really have any more information about it. We just know that we have some number of arrays, and those arrays are some length. And in this case, for the math, for talking about time complexity, I'm going to assume that all the arrays are the same length, but when we're solving the problem, that's not necessarily going to be the case. So that's just like, it's going to be way too complicated if we try and do the time complexity with all the arrays being different lengths. But I'm going to assume when I'm solving the problem that this array could be length 3, and for example, we could have this array here where this would be only length 2. So things to keep in mind, things like that. You might ask any other clarifying questions now, because this is a good time to do that. And once you've sort of clarified with your interviewer, we can just get right into how we might actually solve this problem. And the first thing that I think of that is maybe an obvious solution, but is a solution that's very much worth mentioning, is what if we just combined all of these into an array and then sorted the array? That's a fairly simple way to do this. We know that that's going to give us a fairly good runtime. It's in this case, we have enough the solutions are similar enough in runtime that I'm actually going to go ahead and look at what the runtime would be up front so we can evaluate our solutions. But so let's say we have k arrays of length n. So for merge sort, or any sort of sort, it's going to be the length of the array, it's n log n, right? So it would be k times n, if n is the length of each individual array, times log, so like kn times log of kn, right? And that would be our merge sort, because kn is going to be the length of our new sort of mega array that we've created. And that's fairly good, but we can do slightly better than that. And we know that we have this information that our k arrays are sorted, and that should sort of give you a clue that there may be a better solution other than the obvious solution, because usually they're not giving you this information unless you can use this information in some way. So let's actually think about, how could we solve this in a slightly more clever way? So we have these 3 arrays and we want to merge them together, right? And so I'm just going to spread them out like this, and then we're basically going to construct an array from these. And we know that, let's say we're going to just do this we're going to do it one iteration at a time, obviously. And so in our first iteration, what is the smallest element? And because on our first iteration, we just want to copy the smallest element into our new array. And the smallest element we know has to be one of these 3 elements, right? It has to be one of the first elements in the arrays, because otherwise they're not in sorted order, because we know that the 0th element of each array is always going to be the smallest element, or the leftmost element is always going to be the smallest element. So we can do that, and we take this 1 and we copy it down here. And now what do? We need to actually now what we need to do is we need to compare these three, right? Because we have already added the 1 now, so I'm just going to put like a dash there. And now we would compare these, and then we would copy the 2, and so on and so forth, and we would keep going. And so and then in this case, this next turn, we would need to compare the 4, the 5, and the 3. And hopefully you can see what I'm doing. I'm always comparing the next available element in a given array. And so we could do this in a couple of different ways. The maybe obvious way is just to do this in a turn-based fashion and we could say like create a array of length k where each element in k, the nth element in k is a pointer to the element that we're looking at in the nth array. So for example, let's go back to here. We would have our array would look like 0, 0, 0. And then after the first turn, so after here, it would look like 1, 0, 0. So we would compare the first element, the index 1 element from this array, the index 0 element from this array, and the index 0 element from this array. And that's not a bad way to approach this. That's sort of a naive way to approach this, but it would be totally reasonable. And let's think about what the runtime of that would be. So we have to go through k times n turns, right? Because we have to go add each element to the array. So we're going to have k times n, like we had before. But now we're going to do each of these comparisons. And each of these comparisons is going to be k comparisons, right? So we're going to have to do k amount of work each time that we go through this. And that's actually going to be more work than we had here, right? Because this is going to be k times n times k, which actually it's going to depend on the value of n, right? Because depending on the value of n, one of these might be better than the other. But in this case, it's probably going to be a bit worse in terms of time complexity. So let's just look at one more option. And that option is, and I'm going to copy this down here. So we have a kn times log n option, we have a kn times k option, and then our final option is we could think about other clever things we could do, for example, using a priority queue. And that's sort of the clever approach to this, and this is the approach that I'm going to look into a little bit more here. So let's say that we added all of the first elements of each to a priority queue. So we're going to have 1, 2, 3, and then we just we're basically going to remove all these elements once they're in the priority queue. And we know that to add to a priority queue, it's going to take log n time to add an element to a priority queue. And our priority queue is always going to be of length k, because we're always going to keep in at most one element for each array. So we have those 3 elements, and then we're going to remove the first item from the priority queue and add it to our final queue like this, and then we're going to get the next element in the array that original element came from, and remove that and add that to the priority queue, which is going to take log k time, because there are going to be k elements in the priority queue. So and hopefully this makes sense how this is going to work, because the priority queue is basically going to automatically sort our list of potential next nodes in our array, or next elements in our array. And so the priority queue is going to allow us to basically do that sorting automatically. And if we look at the n for this, we're going to again have k times n because we have k times elements, and then adding to the priority queue takes log n time, and removing from the priority queue takes constant time. So that's going to be times log of k. And so this is going to give us our best solution, right? Because we have kn log kn, we have kn log k, or kn k, or k squared n, and we have kn log k, which is obviously going to be better than this and better than this. So I think this is going to be the best solution, and I'm going to go ahead and actually start looking at how to code this up. And hopefully that makes sense. It hopefully will, if it doesn't make sense now, it should make more sense as we get into actually coding it up. But I will point out that this is a good approach if you're if you can come up with multiple possibilities, and especially if there's some specific information about the problem that you think might be relevant, it's good to try and think of different solutions and maybe just sketch out what the runtime is going to be for each of these possibilities, and that will help you to evaluate what the best option is. Like, for example, you can see here that, because I mentioned earlier, you should see if there's any sort of bounding on k or n. And part of the reason for that is that one of these solutions might be preferable to the other depending on the value of n, for example. But anyway, we're going to go ahead and we are going to, let me get rid of this. And the first thing we need to do is we're going to create a priority queue. And I'm going to use the built-in priority queue class in Java, so I'm not going to implement that manually. But what we do need is we need like priority queue nodes. And the reason for this is that we need more information than just the value. Because what we're doing is, let me put this back here for a sec. This is like this. As we remove elements, we need to know what the next element in the array that one originally came from was. Because when we remove this 1, we're going to then take the 4 and add that to the priority queue. And so we need to know where the 1 came from. And it's not as easy as just looking in all the arrays, because what if we had 1, 1, 3, for example? Then we wouldn't know which array it came from. So we need to we're going to need to track additional information. And the other thing is that, so I'm going to create a node class, but we're also going to have to implement a comparator for that, because our priority queue needs to be able to sort the nodes. And so we're going to need to, since we're putting a custom class into our priority queue, we're going to need to tell the priority queue how to sort it. So let's go get right into this. This is going to get a little Java-y. So if you don't really do Java, you can just sort of sit back and relax for this part, but know how to do this in whatever language you feel most comfortable with. So we're going to have a private class, and I'm going to just call it a queue node. And importantly, it's going to implements comparable queue node. Right? Because this is going to be able to compare itself to other queue nodes. And I'm not going to do anything super fancy here, because you could certainly do much more like proper code, but the point here is really just to get everything out on paper. So if there are things where maybe you should be checking for X, Y, or Z, you can point that out, but it's really not a big deal in this case. So I'm just going to have 3 values. I'm going to have an int array, which is going to be, I'm going to pass in a 2D array that's going to be an array of my arrays. And so the first value is going to be an index of the array. The second value is going to be an index within that array. And then I'm also going to actually have to store the value at that index, because that's what I'm going to be sorting on. So I'm going to have int array, which is going to be the index of the array. Index is going to be the index in the array, and value. And then I'm going to create a constructor for this. Usually I wouldn't create a constructor for some small private inner class like this, but it's going to make the code slightly cleaner later on, especially since we're setting multiple values. So I'm going to go ahead and create a constructor. So I'm just going to do public queue node, and it's going to take in, the 3 values, and it's going to set them. So this dot array equals array. This dot index equals index. And this dot value equals value. So that's going to be our constructor. And then we also need, since we're implementing comparable, we're going to need to implement a Compareto method. And this is something that you may not, I don't know, I wasn't 100% sure on the syntax off the top of my head, so I had to look this up. So it's not something you'd probably be expected to know the exact syntax to in your interview, but it's good to know that this exists and be able to explain what it is that you're doing. And maybe your interviewer will help you along, or maybe they'll say, don't worry about the exact syntax. But just in that case, you really just need to do the best you can. And it's very unlikely that they would dock significant points from you unless you're, applying for some senior Java development position, and you really should know this. So in this case, it's just we implement a public method called Compareto, and it's going to take in a queue node n. And so we're just, in this case, we're going to compare the values. So if value, and obviously, so if the current node is greater than the node that's passed in, it returns a positive integer. The opposite is a negative integer, and then if they're equal, it returns 0. So in this case, I'm just going to return 1, -1, and 0. So if value is greater than n dot value, then we are going to return 1. Otherwise, if value is less than n dot value, we return -1, and otherwise we return 0. So hopefully that makes sense. That's just a very simple way for us to then compare these nodes that we're working with so that we actually know, so that our priority queue is able to treat them in an appropriate way. And so now let's actually get into implementing this. And there are a couple parts, right? So we're going to create a priority queue, and we're going to add the first node from each, or the first element from each array. And then we're going to go through and we're going to remove elements from the priority queue, and using that element, we're going to know what element to get to add to the priority queue next. And we're just going to iterate through the priority queue until the priority queue is empty. Because eventually we're going to, once we get to the end of each array, we're just not going to add a new element to the priority queue. And eventually we're going to run out of elements. So let's go ahead and do that. So we're going to return an int array. And I'm just going to call it merge. And it's going to take in a 2D int array. And I'm just going to call it arrays for lack of originality. And so let's see. So we're going to create our priority queue first. So priority queue of queue nodes, right, is going to be called PQ. And it's a new priority queue of nodes, like that. And then we're going to need to, so we need to actually figure out what the size of our our final array is going to be, because we didn't, so we're assuming that the different arrays could potentially be different lengths. So we're going to need to calculate the size, and we're also going to need to get the first node of each array. So I'm just going to do a loop through all the arrays, and I'm going to kill 2 birds with 1 stone. So I'm going to say int size equals 0, and then I'm going to do for int I equals 0, I is less than, let's see, arrays.length, and I++, and then I'm actually going to, so first I want to check, well, I'm going to first add the size of the array to my size so that I can calculate the total. So that's just going to be size plus equals arrays I.length. And then I'm going to say, I only want to access the first element of the array if the length is greater than 0, because we don't know, in theory at least, even though that would be kind of dumb, there could be a 0 length array in our array of arrays. So we should check the size just in case. So I'm going to say if arrays I.length is greater than 0, then I'm going to add the first node to my priority queue. So I'm going to say pq.add new queue node. And this is where our constructor comes in helpful. We're going to, so the first is the array index, which is I. The second is the index of the element, which is 0. And the third is the, is the value, which we're going to just access, which is arrays I0. And that's all there is to creating this priority queue. That's the first step. And now we're going to need to create a results array where we're actually going to store the results. So I'm going to create this int result equals new int and the size that we just calculated. And now I'm going to go through all of the elements in the priority queue and keep adding elements. And I'm going to go through until until the priority queue is empty. So I'm going to actually do a for loop here, and the reason for that is so you can see I'm going to do int I equals 0 and I++, but I'm going to just create the condition is going to be not pq dot is empty. And the reason I'm doing this is just that it's slightly more compact than creating a while loop and putting a counter in the while loop. And there's not really any reason to prefer one or the other, one over the other, except for the fact that this is like 1 or 2 less lines of code. And it's, of course, so we're, in case it's not, doesn't make complete sense, we're setting the variable I here and we're incrementing it, but our condition for our for loop is just something different, other than some I is less than, you know, some value. And this is, the I is going to be our pointer into our result array. And so it's going to, it makes sense. We want to increment I each time we add something. So that's just going to make it this much simpler. It's really, you know, neither here nor there. But what we want to do is we're going to get our node, first of all. So q node n equals pq.poll. And that's, well, for whatever reason, it's poll instead of remove. So go figure. And then we're going to, first off, we just want to set our result to be equal to the value of n. So that's all fine and well. And then what we want to do is we're going to check if the, so we want to check whether that was the last element in its array. And if it's not, we're going to add the next element. And otherwise, we're just going to skip over it. So I'm going to create a new index, which would be like the index of the next element, is n dot index plus 1. And then I'm going to say if new index is less than arrays n dot array dot length. Right, so if the new index is less than the length of the array that we're referencing, then we know that there's another element in the array. So hopefully that's pretty self-explanatory. And then if that's the case, we're going to add a new node to the priority queue. So pq.add new queue node n.array new index and arrays n.array and new index. So let me actually, right, so that's going to be our result. Well, that's going to be the rest of the code, and then we just need to return our result array once we're done. So we're going to return result. And so hopefully this makes sense. We're just adding all the elements to the priority queue, which is sorting them when we add them, and then we're removing them in order. And by adding them to the priority queue, we can add them in order in log k time. And so it's going to be slightly more efficient. And let's just go through a very, very abbreviated example of this. So I'm going to just say we have 1, 3, and we have 2, 4. Actually, I'm going to say we have 1, 3, 5, and we have 2, 4. So these are good. These are going to be our 2 arrays that we're adding to. So we create a priority queue, and so PQ is going to be an empty list for now. And then we're going to, so size equals 0. And now while I is less than arrays.length, which is 2, we're going to say size plus equals array I.length. So size plus equals 3. And then arrays I.length is greater than 0. So we're going to say pq.add new node I0 arrays, which is this one here. So we're going to have a new, it's going to be I is 0 and 0 and 1, like this. And then we're going to go, so we're going to increment I, size plus equals 2, so size equals 5 now. And then we're going to add another element to our priority queue. So we're going to add, it's 0, or it's 1, 0, 2. So now we're going to come down here, we're going to create our result. So result equals this array that's going to have 5 empty slots in it, and I equals 0. So we're going to say Q node, we're going to get the first node, which is this one. and we're going to set the value to be equal to or we're going to set result I, which is 0, to be equal to the value, which is 1. And we also remove this from here. And then we're going to say new index is n.index plus 1, which is going to be 1, right? Because the index was 0. And we're going to create a new node, which is going to go here. Because it's going in sorted order. So it's going to be 0, 1, and 3, like this. And then the next, we're going to loop again. We're going to remove this. We're going to add 2. Sorry. We're going to add 2 to this, like so. And then we're going to get the second, or the index 1 element of this second array, which is going to be 4. So we're going to add to here, we get 1, 1, 4. And we're going to add, and then we're going to keep going. We're going to remove this. We add 3 here. We add 0, 2, 5 here. And then we're going to remove this and add 3. And now next index, add 4. And now next index is equal to 2, and 2 is not less than arrays.n.array.length. 2 is not less than 2. So we're going to skip this and just come back to the top, and we add this last one. We add 5 here, and we remove it, and now our priority queue is empty, and so we're going to return the result, which is this. And so obviously I went through that very quickly, as I usually do, but hopefully you'll have more time in the interview where you can go through it in a little bit more depth. And that's really all there is to this. I think it's a pretty cool problem. There are a bunch of different ways to solve this, all of which are pretty good. And so if you didn't get this solution, don't feel bad about it, because there are a lot of good solutions. But, it's a pretty popular problem to ask at like Google or companies like this. So hopefully that made sense. And if you have any questions, let me know in the comments below or on the blog. And I'll see you guys again next week.